So what we were doing yesterday, we used kind of this area model to where if I had you do x plus an 11 multiplied by an x minus a 12, we put the x minus 12 on top, the x plus 11 on the side. We multiplied just with the idea of an area of a rectangle, the length times the width. We got all these four unique boxes. And we talked about if I want the area of the overall box, then we would want all of these things added up. So then that's what we did over here. They always had like terms. We simplified those by adding our like terms. That would give us our area. What we then kind of settled into, in the area model here, these rectangles are still going to be pretty important. We're going to use those quite often throughout the module. But we then wanted to transition to, we don't want to have to draw that out every time for something like this. What really happens in that area model is this first term here just gets multiplied by both terms in the second quantity. So we're basically distributing that 4x to the second quantity. And then what is somewhat new for you is we have to distribute again the second number in that first quantity to every term in the second quantity. So you're really kind of double distributing. All right. And that's sort of what the area model showed us we were going to be doing. So when you get to number 7, if we understand sort of what this notation means, don't write this down, but if I gave you 9 squared, I think we all know that means there's 2 9s being multiplied by each other, correct? So if I now put that quantity squared, it means the exact same thing, but with that quantity. So if I give you 2x plus 5 squared, that simply now means I have 2x plus 5 multiplied by another 2x plus 5. We could set up the rectangles if you wanted. And again, we are going to use those further. But what we kind of want to get to is something like this, is just understanding I'm going to take this 2x right here, and it's just going to get distributed to both terms in that other quantity. All right, so we'll carry that out. The 2x multiplied by a 2x, the 2 and the 2 make a 4. X times the x gives you x squared. And then that 2x then gets multiplied by the second term in that second quantity, which is a 5. So 2 times 5 is 10. And then there's an x attached to that first one, so that's a 10x. Once we are done with that, then we've got to take 5, and that 5 is going to get distributed to each term in that second quantity. So from there, we're going to do 5 times 2x, so that's a 10 with an x attached to it. And then 5 times 5, which is a 25. All of them so far, and this one is no different, have like terms. So we now can look right here. These are our like terms. We're going to be able to add those together, combine those. So I'm going to write 4x squared, add up these like terms right here. We have 20x terms, and then that constant 25, and then that's our answer. All right. Good with that? Easy enough. Okay, then go to the next one. This one I do want to set up the area method just so we see how this would play out. But understand how this one is now a little bit different. This is now, you have 1, 2, 3 terms, and it's being multiplied by 1, 2 terms. So when we set this up, do it this way. So kind of draw it vertically a little longer. And then break this into thirds, and then cut those in half. The reason we want 3 here is because that's how many terms we have here. So I'm going to take this 4x squared, and I'm going to put it right here. I'm going to take this negative 7x right here. So then we would have subtracted 7x. And then we're going to take this plus 2, and I'm going to put it right there. So since there's 3 terms, that's why I would have 3 vertical rows. And then on top, we just have the 2. So I'm going to put a 3x plus an 8, or 3x and an 8. Now, before you do it, just hang tight, get that all set up. Because again, long term, we don't really want to have to do the boxes. We can just jump right to this right away. So watch how this would now play out. If I'm going to do this, wouldn't this box here, oops, wrong one. If I ask you for the area of that, wouldn't that be the 4x squared times the 3x? So when we do that, actually do that. Tell me what you think that equals. There's one little element here I want to see if we understand. All right. We should all know, I would hope, I'm pretty sure we know, that 4 times 3 is 12. So that's easy. All right. And then what do we think x squared times x is going to give you? Joe? Good. That's x cubed. All right. So that should be 12 and then x to the third power. The next one, same thing. If I now ask you for this row, you would take 4x squared and multiply it by that 8. So 4 and 8 make a 32. And then there's just the x squared. Before you go any further with that area problem, think about what you just did. Didn't we just take 4x squared, multiply it by a 3x, and then we took that 4x squared, multiplied it by that 8. So if we go back to this, now that we have 3, all we really did is took this 4x squared, multiplied it by 3x, just like we did here, and we took this 4x squared and multiplied it by an 8. So if we do that now over here as well, if I did 4x squared times 3x, that would give me that 12x cubed that we got in this upper left-hand corner. That 4x squared multiplied by that 8 then gives us a positive 32x squared, just like we got here in the upper right-hand corner. Let's revisit that area model. If I now took this, if I now asked you for the area of this little rectangle, wouldn't I have taken a negative 7x times 3 to get a negative 21x? And then take that negative 7x times 8 to get a negative 56x. But again, all we're really doing is taking this negative 7x, multiplying it by that 3x plus an 8. So couldn't we just do that over here? Take this negative 7x, multiply it by 3. That would give us the negative 21x. And then the negative 7x, negative 21x squared. And then the negative 7 times 8 would give us a negative 56x. Then you can do the area model if you want, but wouldn't these two boxes down here now just be this 2 distributed to both the 3x and the 8? So that's all we're going to do here. Take this 2 and distribute it to the 3x and the 8. So 2 and 3x make a 6x. I may have to erase this a little bit here. Writing too large. And then the last term, that 2 times an 8 is a 16. That would have been the same exact stuff we would have gotten in here. So now you're just basically distributing 3 times because we had 3 terms in that first quantity. Okay. Add up all your like terms. So here's an x cubed. There are no other x cubes. So that we're going to drop down. And then we're done with this guy. We do have a few x squareds. So here are the x squareds that we're going to combine. So we have 32 here, take away 21 of those. That leaves us with 11x squared terms. Then our x's, we have a negative 56x and a positive 6x. We combine those to be a negative 50x. And then our constant is all by himself. He has no like term that he can be combined to, and that would be our final answer. Okay. All right. So that's that stuff. All right. At the very end here, I think you've been exposed to this. If not, it's super easy. X-intercepts. So if you look at this red graph, when it asks you for the x-intercept, we all know this is your y-axis, and we should all know that this is your x-axis. X-intercepts are simply when this parabola here crosses the x-axis. So watch where this parabola hits the x-axis. That should happen twice, right? Here's one place where it crosses. Here is the other. So what I would just have you do then, the x-intercepts are different ways, depending on what we're looking for. I'm going to have you write these as points right now. And the first point is 0, 0. That's where we cross the x-axis. Then just label the second point, whatever those coordinates are. That point has an x coordinate of 2, y coordinate of 0. Those are our two x-intercepts. Second one, kind of a trick question. Where does that parabola cross the x-axis at? Joe? Nowhere. So there are none. So if I ask you how many x-intercepts we have here, clearly in the first one we could have 2. The second one we don't have any. There aren't any x-intercepts. If I go to the third one, we're back to 2 of them. So we just label these 2 points where we cross the x-axis at. Well, you can't really see that good. All right, so this is going to cross 2 different times. One of them is, let me put it above, the coordinates 1, 0 is our first one. The second coordinate pair, 3, 0. So again, we've had 2 intercepts, we've had no intercepts. The other thing that could happen with a parabola, if we look at this guy, how many times does that one hit the x-axis? Yeah, just once, right? So whatever that is, that looks like it's at -2. We could also just have 1 x-intercept. So we can have none, you can have 1, you can have 2. Okay. Okay, so that's yesterday's note. So now pull today's out. The one that I just handed out. If I can find it. And this should go hand in hand with what we just finished. All right, so it says when we square this binomial, so binomial, I've thrown around a little bit that word bi, meaning kind of bicycle. All right, 2, that prefix means 2. So binomial, there's 2 terms here, x and a, and then we want to square that. All right, so we're just going to square this binomial. The result is what we call a perfect square, and then we all know the prefix, hopefully tri means 3. So if I square a binomial like this, it should actually produce a trinomial like this. Okay, and we're going to show that down here. So it says use an area model to represent each of the following. So go ahead and draw in an area model. So make a square, rectangle, whatever, cut it in half in both directions.
This way.
Yeah, did you not get one? Yeah, that's it. All right, then yesterday. So let me just pull up a blank one. Yesterday, if I had done this, we weren't necessarily worried about drawing these to scale, but if I had done x plus a 1 times x plus a 7, and this is your length and this is your width, wouldn't our width be longer than our length? So if we were to really kind of sketch this in accurately and to scale, we'll say our length is x plus a 1. So what should happen is x and a 1 should be shorter than the x increased by 7. We should be longer widthwise than we would lengthwise. So most of these are rectangles is what we're dealing with. Well, if these are the same, so if I now go back to this, wouldn't this just be x plus 7 times x plus 7? So both of these would be identical. If that's an x and a 7, and this is an x and a 7, this is now truly a square. We have the same length as we do our width. All right, that is why when we eventually do this, we're talking about a perfect square because the length and the width are the same, okay? So let's fill these in. The x and the x, we seem to have a handle on this pretty well yesterday, is x squared. The 7 and the x would make 7x. 7 and x again make another 7x. And then this bottom right-hand corner is the 7 times the 7, which is a 49. If we do it right, what I'm telling you up here is in the setup of this problem, when I square a binomial, I should produce a trinomial. So if we now add all these up, so you're going to have your x squared. Notice again, not coincidentally, and this is something we want to recognize, these 2 corners we can add up. They're like terms, so we're going to have 14 x's. And then that constant 49 is the lower right-hand corner. What should have happened has happened. When I square a binomial, I should get a trinomial. Okay, and that's what just happened. So real quick, because I think you can do this on your own now. This is not necessarily hard, and yesterday it seemed like we were getting it. Do letter B, see what we get. Go ahead and set that up. We should get a trinomial out of this. I do want you to use the area model though. And since it's a square, try as best you can to make it look like a square, because the top and the side should be the same lengths. All right, so do that, add them all up. Should get a trinomial out of it. All right, Jake, what do we have for this corner right here?
X squared.
Good. Upper right-hand corner,
10x.
this corner,
10x.
and the bottom right.
100.
Good. All right, so if we're just finding the area of each of those, x squared, and then we get two 10x's, we get 100. Again, these are like terms. So as we simplify this, add them all up, the x squared would be by itself. 10x and 10x added together is a 20x, and then plus a 100. Now, what I want you to recognize about these is going to be really, really important on the next page when it gets a little bit trickier, is that these, again, are called perfect square. Let's make that a t, perfect square. And remember, this word square means our length and our width are the same. So that's why x plus 7, x plus 7, x plus 10, x plus 10. That's the idea of a square. And these are called perfect square trinomials. So when we reference that, that's what these area models would always look like. So in a perfect square trinomial, what we want to recognize is when we look at what I have highlighted here in red, not only are these like terms, they're both x terms, aren't they the actual exact same number as well? Okay, not a coincidence. So in a perfect square trinomial, you're going to get 7x here, if that's our value, and then 10x, 10x, those are identical. So in number 2, it says when you square that binomial, what do you notice about the b and the c to give you this? So if I gave you x squared, so that's this guy, and then it says bx was a 14 in this problem, and then plus our constant, which is the 49 in this problem. How could we get those quickly without doing our area model? That's what this is kind of looking for. So if we don't want to have to set this up all the time, if we don't want to rewrite this all the time, there is a nice little shortcut. If we just look at this little pattern, that would take us from here to here very quickly. All right, you can't really see it that good yet. All right, let me make it smaller. So what do we notice about that? What's a pattern that we see there? Done.
It should be added by itself and then times itself.
Okay, I actually really like that. So the B, he said, is added by itself. And then he said the C is multiplied by itself. Now we want to define kind of what it is, added by itself and multiplied by itself. So if we look at this, what was added by itself and multiplied by itself up here, Ben? What number?
7.
Yeah, so this 7, if I just did 7 plus 7, doesn't that give us the first term when he says that you're going to add it by itself? And then if I took this 7 and I multiply it by itself, wouldn't 7 times 7 give you that 49? Okay, so real quick, if we understand what Ben just said there, let's write this as x plus a 4 and tell me very quickly what this trinomial would be without doing the area model, without rewriting it and multiplying everything out, combining our like terms. We can write that, actually put a square here, that's important. If we understand what we just talked about here, what would x plus 4, the quantity squared, give you? And then very quickly, hopefully. Anybody got that? What should this look like? Yeah, Kara?
X to the second plus 8x plus 16.
Good. And did you just kind of do what we just highlighted here, what Ben said? Yeah. So you take 4, add it to itself. That's going to give you the middle term. You take 4, multiply it by itself. That's going to give you that outer term. Okay? Good. All right. The next one then. Only difference here is, see how these are all pluses, x plus 7, x plus 10. These are now x minus 8, x minus 11. So let's use our area model first to see if this is going to kind of follow the same pattern. These are squares because it's the exact same thing. There's an x and a negative 8 for your width and an x and a negative 8 for your length. We'll fill this in normally. Let me make this bigger. It's kind of blurry when it's small. So this would give you x squared. X times the negative 8 is the negative 8x. Same here, the x and the negative 8 would make a negative 8x. And then the negative 8 times the negative 8 gives you a positive 64. So what this should give us is this x squared here. Notice again, like terms, and not only are they like terms, they're identical terms, so that we have a negative 16x. And then bottom right-hand corner is that 64. So let's see if we use Ben's thought here. If I took this number, and now you just have to understand the fact that this is a minus 8, if I did a minus 8 and I add another minus 8, would that give us a minus 16? Yeah. And if I did a negative 8 times itself, does that give us this positive 64? Yeah, so is it the same exact rule? Yeah, same rule. We just have to understand if it's a minus, then this sign is going to be minus. And if it's plus, then this sign is going to be a plus. So without any work, write down letter B. So what is that going to equal? No area model, no rewriting it out, distributing, combining like terms. We should be able to go right to that. All right, Julia. What do you got, Julia?
X squared minus 32x plus 22y.
Good. So take a negative 11, add it to itself. Negative 11 and a negative 11 will give us the middle term. A negative 11 times itself will give us that positive 21 term. Okay? All right, so those are, again, perfect square trinomials. So keep that in mind. Go to the next page. And this will challenge you a little bit differently. And we'll kind of see if we can think through this. So we can make this nice and big. All right, this says find the missing value that would make each trinomial a perfect square trinomial. All right, each trinomial a perfect square trinomial. So if you look at letter A, to start this off, and you don't necessarily have to draw an area model for all of these. You don't really want to have to draw it all, but we are going to be for this first one. So since it's going to be, remember, a perfect square, try to draw your area model as a square. So they have the same length and they have the same width. What we hopefully know at this point is this x squared term goes right here. And the only way we would have gotten that is by multiplying an x by an x. If I go back to that previous page, notice how this middle term, the way we got that middle term is from these two corners, and aren't those corners the exact same set of numbers? If I go to the previous two, the way we got this middle term, 14, is because we had 7 in one, 7 in the other. And the way we got this 20 is because we had 10 in one and 10 in the other. So the problem that we are working on, if we know that we have 6 as the middle term, write down, don't say it, see if we understand this, write down how many we know we have in those two corners. If you now know that, so if you were able to write that down and understand what we should have had there, then now write in the number that had to have been right here and right here, so that we got these two terms. And if you know that, then we should be able to answer this question, because whatever this bottom right-hand corner is, that's always this number at the end of it. See if we can put all that together. All right, see him?
Are you calling?
I thought you raised your hand. You're scratching. I got an itch. Yeah. My hair gets in my eyes all the time too. I do that and it's itchy bad. So I can sympathize with you. All right, these two corners. Do you think you know those, Sehan?
Yeah.
Okay, what do you think are these two then?
I put 3x.
Good. Do we agree that these would each have to then be 3x? Because they have to add up to be that middle term. Well, if each of these are 3x, what did these two places have to be, Sehan?
3.
Good. These would have to be a 3 and a 3, which means what is this number here? 9. So to make this a perfect square, we would have had x squared plus 6x plus 9. If you then look at what we would have multiplied, wouldn't we have had an x plus a 3 multiplied by an x plus a 3? So we would have had x plus 3 squared. And if we do our shortcut with this, it better give us the one that we started with. Okay? All right, B. I am again going to use the area model to start this one. Long term, if you want to use it, it is totally fine. But we would long term like to not have to use it. So now the x squared is right here. So x and x gives us this x squared. We now know this is a 100 because that's your constant. So now we did this a little bit yesterday, but now this has to be a perfect square. So we need to get the same numbers here as we do here. And we better get a 100 for the bottom right-hand corner. So right now we think that's going to be. Okay, anybody got that? I think. Matthew? What is it? For both?
Yeah.
All right, so if I have 10x here, 10x here, so what do you have up at the top, 10 also? What do we then put into our blank here, Matt? Good. That would have to be a 20x because it is the sum of those two. Okay. So now, letter C. Let's say we don't draw this out. Letter C looks like this first one. So don't we know in a perfect square trinomial that whatever this middle number is, doesn't half of those go into this corner and the other half go into this corner? So aren't we really just cutting that in half, assigning some of them to the one spot, some of them to the other? So if I had 18 total, maybe I lied. I'm going to draw this one more time. So we know this is our x squared. So this is x and an x. So if I know I have 18 total, half of them have to go here. Half of them have to go there. So Armando, that means how many are in each of these?
9.
Good. So we'd have 9 here, 9 here. So that puts a minus 9 on top, minus 9 on the bottom. So if we divide that by 2, isn't it then going to be 9 and 9 multiplied together to give us this bottom number? So that this would have to be 81. Okay, following that? All right, then I'll give you a few minutes. Actually, I won't because they get a little different. Do D. See if we can do D. D should be a nice one. And then E and F, little tweaks. D, E, and F, both. Well, E and F especially, but D. Anybody think they have D? Feeling clever. Omar, what do you think, Omar?
24.
All right, Omar says 24. Do we agree with Omar? All right, good. If you got 24, you did that correctly. Because if this is 144, the only way that these could have been the same and multiplied to be 24 is if I had a 12 and a 12. And then the 12 and the 12, add those up, should be your 24. Okay? All right, now let's see who's clever. Letter E. Do letter E. Yeah, Matt, question?
I was gonna say the
Oh, okay. Hold on just a second. So letter E and F, little sneakier. Little sneakier. And again, right now, if you need to draw the area stuff, go ahead and draw them in. It's a nice tool to have and use. Yeah, we might need calculators here. It's probably a good sign if you're pulling out your calculator right now. All right, Matthew, you confident in this?
five.
5, you said? All right, Matthew says 5. Do we agree with that? Omar's not so sure. What do you have, Omar?
Isn't that decimal?
Maybe. What'd you get?
6.25.
Omar gets 6.25. Anybody agree with that one? Got a couple head nods there. Omar, how'd you do it?
2.5.
And where'd the 2.5 come from?
X was 2.5.
Okay, so doesn't this 5 have to be gotten from these two corners added up, and half of them go in one corner, half go into the other? So what we're really doing with all of these is I'm cutting this in half. When I do that, I would have 2.5x's here and then a 2.5x right here. So what that means is the x squared, we had x and x's, and then I would have had on the top a 2.5 and a 2.5 here. So the way he got this 6.5 isn't 2.5 times 2.5, and that's why I was saying if you're pulling out your calculators, that's probably a good sign because we may not know what that was. And the 2.5 times 2.5 would give us 6.25. Okay. So a little sneakier when you don't get a nice whole number there. Okay, F. Sneakier yet. Let's see what you think for F. This one you may want to do the area square model. Otherwise, it's pretty tricky. Okay, this one I'll be impressed. Anybody feeling clever this morning? We'll throw this out there. Joe, what do you got, bud?
-5.
For right here?
Oh, the answer is 10.
So you got 10 right here.
Yeah.
All right, do we agree with Joe? Everybody? No, who said that? What do you got? You got 20?
I think I did something wrong.
All right, let's use our area model to find out then. Okay, one of those two is correct. If I'm going to get 4x squared now, if I were to ask you, and remember these are squares. Squares have to be the identical length and width. So this number and this number have to be identical and multiply to be 4x squared. So the only way that's possible is if these are both 2x and 2x. All right, agree with that? Same thing with that 25. To get a 25, these have to be identical, right? Because it's a square. These lengths are the same. So if these are the exact same numbers and they multiply to be 25, then I think we would all know those have to be 5s. Now I'm going to erase both of these. Everybody do it again. And then determine which one is right. Because now all we need to do is figure out what are these two numbers, add them up. That's got to be this middle number right here. So if I told you to finish this corner, add those two up, that's got to be the middle number. All right, when we do that, Joe L, what do we actually get right here, Joe?
5x.
What is it?
5x.
Look at what we have here, right? Isn't this length?
10x.
Okay, so this one is a 10x. If I look at this little rectangle down here, Joe, isn't this 5 and a 2? So this is going to be what? Yeah, so each the 10 that Joe gave us, that's what each one of these is going to be. So the middle number then should be these two guys added together. So we wanted to do 2 of those 10. So yeah, 20 ends up being the correct middle number in this case. It gets a little sneakier when this number right here isn't a 1. Okay, so just kind of be aware of that. That's why these are still nice. These little area squares are nice for something like that. Okay. Okay, real quick. Here's what these are now asking. Actually, you know what? Let's do these first. Do 1 and 2. These are nicer. Actually, the first 4. So go to the bottom. Do 1, 2, 3, and 4 at the bottom while we have a minute. These should all be somewhat nice. If we can do these, if you're understanding, these should be quick ones. On the north side. Okay, with these now, if we were to set this up, and again, some of us are, some of us aren't, you do what you need to do. If we had 18 as the middle, doesn't that mean I had 9 and 9 in those corners? So that means I would have had a 9 and a 9 getting multiplied together to give us that bottom right-hand corner. That's got to be 81, okay? So if we start kind of understanding our little shortcut, aren't we really just taking the middle number, cutting it in half to get the 9s, and then I'm doing 9 times 9 to get this last number. So here, if I had 10 total, doesn't that then mean we had 5 up here, 5 right here? So that when we multiply those, that last number has to be a 25, right? Okay, next one, 3. Omar, what'd you get for 3, Omar?
169.
Good, 169, because we would have had cut those in half, 13 in each corner, and then 13 times 13 is 169. Jada Robin, what'd you get for number 4, Jada? Good. Cut these in half. We have 8 in each corner. 8 and 8 gives you 64. I didn't tell you to, but a lot of us had kind of worked ahead to this. So if I gave you this one, it's pretty much the same as this one, isn't it? Pretty darn close. If I give you this one, Lily, did you do this one yet? Good. That's got to be 81 because we would have cut that in half, 9 in each corner. So then 9 and 9 make 81. And then Armando, number 6. How many would we have here? Good. We would have had 24. Half of them go in the corner on top, half go in the bottom right-hand corner, and then the 12 and the 12 give us 144. Okay? Okay. Following all that. Okay. Last thing, go to A. I just want you to see this. If I ask you to rewrite this as a perfect square, we're kind of going backwards from what we started with. So if I ask you what the measurements of this would be, wouldn't this have been x and an x to get x squared? A perfect square means these have to be identical. And when we multiply them out to get these 3 remaining rectangles, have to have the exact same number here. So what numbers or number would that have to be, Matthew? 4 and 4, because then 4 times 4 is 4x. The 4 and the x make a 4x, and then that 4 and 4 make a 16. Now, what you want to be careful of is, see how this is a negative 8x? So we really want these 4s to be negative. And then it's a negative 4x, negative 4x. Here's what it means to rewrite these as a perfect square. Notice how this is x minus 4x minus a 4. That's just asking you to write it as x minus 4 squared. We have 2 of them multiplied by themselves, so it's x minus 4 quantity squared. All right. All right, letter B. Wouldn't this, if I cut this in half, had to have been an x plus a 13 squared? And then 13 times 13 would have given you 169. Don't worry about C. Those are tricky right now. We won't make it any harder than it needs to be. All right. Okay. You are not spared homework tonight, so you do have some of that. And you're doing just 1 through 15. So I just want to see one of the ones on the back. So do all the first page and then refresh your memory a little bit on the one on the back. All right, 15 on the back. Okay, back for that. I'll collect tomorrow. This.